Next, we have to discuss the topic power in AC circuit. As we know, in case of AC circuit, the power can be measured as the average power dissipated or developed during an AC cycle. One complete AC cycle is considering if the P prime is the instantaneous power, then the average power during one AC cycle is given by 0 to T P prime dt divided by 0 to T dt, where P prime will be equal to E prime into I prime. In this, E prime represents the instantaneous value of EMF and I prime represents the instantaneous value of current. So, in this method, we can find out the power in AC circuits such as or type we have already discussed. Now, we can start from the pure resistive circuit. As we know, in case of pure resistive circuit, there is no phase difference with the EMF and current. So, E prime is equal to E0 sin omega t, I prime is equal to I0 sin omega t, which implies P prime is equal to E prime I prime, that is equal to E0 I0 sin square omega t, or E0 I0 into sin square omega t can be written as 1 minus cos to omega t by 2. So that now we can apply to this integral to find out the average power dissipated or developed during one complete AC cycle. That is 0 to T P prime dt divided by 0 to T dt. In this, P prime is substituted like this. So, by substituting in this power equation, it will be 0 to T 0 is 0 by 2 into 1 minus cos to omega t dt divided by denominator. We can split this 1 minus cos to omega t like this. And when we substitute the complete cycle for this cos to omega t, after integrating it will be having cosine term, sine term, and it will be vanishing when the limits are provided. So only the existing term is the first integral and the denominator. So it will be having the value t and it also will be having the value t, that is E0 I0 by 2 t by t, that's equal to E0 I0 by 2. So E0 I0 by 2 can be written as E0 by root 2 into I0 by root 2 to write in term of ERMS into IRMS. Impedance can be written as ERMS by IRMS, that is ERMS is equal to IRMS into Z. Power is equal to IRMS into Z into IRMS when we substitute for this ERMS from this. That's equal to IRMS square into Z. Then we got a similar equations as I square R in the general power equation. That's the expression for power, average power dissipated or developed in the pure resistive circuit. This is the power in a pure inductive circuit. That is, we know in inductive circuit EMF is equal to E0 sin omega t and the current is lagging the EMF by an angle pi by 2. So we have to substitute these two terms in P prime, that is like this. We can expand sin omega t minus pi by 2 as sin omega t cos pi by 2 minus cos omega t sin pi by 2. That's equal to, when we substitute the value of cos pi by 2, here we get 0 and here we get 1. That's equal to minus cos omega t. Minus E0 I0 sin omega t into cos omega t. That can be written as sin 2 omega t by 2. That is minus E0 I0 sin 2 omega t by 2. So, P is equal to P prime dt divided by 0 to T dt, which is equal to 0 to T minus of E0 I0 by 2 into sin 2 omega t divided by this integral, that's T. As we know, when we find out or work out for a complete period 0 to T sin 2 omega t, its value will be 0. So, this term is vanishing, which implies that average power in a pure inductive circuit is 0 even though the current is passing through it. This current is known as the wattless current and it cannot provide any power. So, this is why a choke is preferred in regulating AC flow. Actually, choke is an inductance coil which cannot absorb any type of power. At the same time, because of the reactance, it can control the current flow. That's why the application of choke coil. So, once more, the average power in a pure inductive circuit is 0 and that is known as the wattless current. Next is pure capacitive circuit. In this, we know current is leading the EMF by an angle pi by 2. That is, when you substitute here sin omega t plus pi by 2, which you can simply substitute as cos omega t. That is equal to sin omega t cos omega t is equal to sin 2 omega t by 2. When we substitute here, as in the previous case, we know 0 to t sin 2 omega t will be vanishing. So, the power in a pure capacitive circuit also will be 0. This power in an LR series circuit. That is, when we consider in an LR series circuit, the EMF is E0 sin omega t, and the LR circuit, the current lags behind the EMF by an angle phi in phase. So that P prime is equal to E0 sin omega t minus phi. By expanding this sin A minus B form, we can write it as sin A cos B minus cos A sin B. And multiplying with the sin omega t, that is sin square omega t cos phi minus sin omega t cos omega t sin phi. That is, here we can substitute, as we have to apply this for an integral, we have to substitute into the first order term. So, sin square theta is equal to 1 minus cos 2 theta by 2, and also sin omega t cos omega t is equal to sin 2 omega t by 2. We have substituted these two in these corresponding terms. And the next is, we have to substitute here, that is 0 to t p prime dt divided by 0 to t dt. 1 minus cos 2 omega t cos phi dt minus integral sin 2 omega t sin phi dt by t. So, when we substitute that as, by splitting 1 minus cos 2 omega t into cos phi, we can write it as cos phi dt minus this integral cos 2 omega t cos phi dt minus integral sin 2 omega t sin phi dt. As we know, you have to integrate the cos 2 omega t in this term and sin 2 omega t in this term. These two will be vanishing, and only remaining will be the first term. So, cos phi E0 I0 by 2 can be taken outside, and the denominator we got as 1 by t, and remaining is equal to 0 to t dt, that is here. That is, p is equal to, this t and t got cancelled, and the remaining E0 I0 by 2 cos phi. That's equal to, we can rewrite that as ERMS IRMS into cos phi. We know cos phi is the power factor, which is equal to r by root of r square plus xl square or L square omega square. Now we can derive the power, average power dissipated in a CR series circuit. As we know, the current in a CR series circuit is leading the EMF by an angle phi. So, P prime is equal to E0 I0 sin omega t plus phi, E0 I0 sin omega t cos phi plus cos omega t sin phi, and we have to expand as in the previous case, and also sin square omega t is equal to 1 minus cos 2 omega t by 2, sin omega t cos omega t is equal to sin 2 omega t by 2. So, when we substitute in this equation, so when we expand and substitute, first term including integral 0 to t cos phi dt, and here cos 2 omega t cos phi dt, and here sin 2 omega t sin phi dt. As we know, 0 to t cos 2 omega t will be 0, and 0 to t sin 2 omega t also will be 0, and the remaining is first term. So, we have integral dt here and integral dt here, so t by t, and the remaining is ERMS IRMS cos phi, where the cos phi power factor is r by root of r square plus x square. The difference in case of CR and LR circuit is in the expansion of power factor cos phi. Power in an LCR series circuit, that is E is equal to E0 sin omega t, and the current is lagging by an angle phi. Substitute here and expand sin A minus B form, and average power is, here we can write it as E0 I0 sin square omega t cos phi minus E0 I0 sin omega t cos omega t sin phi. That is, here we can substitute as 1 minus cos 2 omega t by 2, here as sin 2 omega t by 2. Here also we have the second term and third term vanishes as in the previous cases, and the remaining is 1 by t E0 I0 by 2 cos phi into t got cancelled. So, P is equal to E0 I0 cos phi, that is E0 I0 by root 2 into root 2 cos phi, that is ERMS IRMS cos phi. Here is also the different term is the power factor for the concerned circuit, that is r by root of r square plus L omega minus 1 by c omega whole square. So you all remember the power dissipated or the average power developed in a CR, LR and also LCR is same by equation, that is ERMS, IRMS into cos phi. But the difference is in the cos phi. In case of LR circuit, it is R by root of R square plus XL square. For CR, R by root of R square plus XC square, and cos phi this term. Graphical representation of instantaneous value of current and power of an AC cycle. For that, we have considering the pure capacitive circuit as an example. For that, EMF is leading the current, lagging the current by pi by 2. So it will be equal to P0 equal to, we know, P prime is equal to minus E0 I0 by 2 sin 2 omega t by solving this. And after that, P prime is equal to P0 into sin 2 omega t. As we know, E0 I0 by 2 is the power, average power. So power frequency is equal to 2 into current frequency. So in this is the graphical representation, and this is the graph which shows the current, and this is the power. That is, we know power frequency will be having 2 into current frequency. That's why the figure is like this. Power factor correction. As we know, power factor of an AC circuit is cos phi, and phi is the phase difference between the instantaneous value of EMF and current. In case of an LR circuit, cos phi is equal to R by root of R square plus XL square. As we know, in case of electric motors and solenoids or other any electric equipments like which you have windings of very large inductance is used. So when the inductive reactance is very large, practically in these experiments, in these equipments, cos phi will be very low. That means energy loss will be very high. So we have to reduce this highest quantity of inductive reactance. For that, the practical case, there is a solution such as a capacitor is connected in parallel with the inductance. Then here the cos phi will be XL minus XC whole square. So the power factor reduction can be managed by connecting a capacitor across the inductance, and in a AC circuit such a way, by connecting a capacitance in parallel with the inductance, we can improve the power factor. This is the method to improve the power factor, and this method is known as power factor correction. Thank you.